Hello everyone, this is Alshar Ahmed and this is my assignment 3 video. I will be walking through two parts. Part A covered 2D image convolution kernels and part B covers training a CNN on the CIFAR10 dataset. Let's get into it. So the first things I want to address is like I face an error. So this happens because ski image I didn't had the SkiKit image installed. So I installed it and then I start the part A. So part A is about understanding how 2D convolution kernels work. A convolution works by sliding a small matrix called a kernel across an images. At every position, we multiply the kernel values by the pixel values underneath, sum them up, and that becomes the new pixel value in the output images. The kernel is what controls the effect, blurring, sharpening, edge detection, line detection, and so on. In this notebook, we load a car image, convert it to a NumPy array, and extract just one color kernel to work with. Uh, we then pad the image with zeros around the border so the kernels can cover every pixel including the edges. This is called zero padding. And for question A, 1A and 1B, I had to create kernels for 45-degree and 135-degree. So for 45 degrees, I used kernel 45 kernel underscore 45 equals nb dot area minus 1 2 minus 1 2 minus 1 2 minus 1 matrix. So the it so after running that, it's diagonally from bottom left to top right. That's our 45-degree direction. For 145-degree direction, I used kernel underscore 135 equals np dot array 2 minus 1 minus 1 minus 1 2 minus 1 minus 1 minus 1 2 matrix. After so the top left to it turns from top left to bottom right. Now you can see in the output how each kernel highlights different diagonal edges in the car image. And next for next one, question 2, three edges kernels were applied already sorry, three edges kernels were already provided. I just applied them and plotted the result. Kernel 1 detects diagonal edges, uh, bright in one corner, dark in the opposite. Kernel 2 is the Laplacian, detects edges in all four directions. Kernel 3 is the full Laplacian, includes diagonals too, so it picks up finer details. Kernel 3 produces the sharpest edge map because it considers all 8 surrounding pixels. And next, part B. In part B, we train a CNN on CIFAR10, 60,000 color images across 10K classes like cars, birds, and cats. And if I go to question 4, question question 3. So the question was, did the network present signs of overfitting? So the answer was yes. Looking at the accuracy curves, training accuracy keeps climbing in blue, but validation accuracy in red starts flattening around. It approaches 15 to 20. That gripping gap in the classic sign of overfitting. And for question 4, the answer is the model has 5 layers. Con 2D, max pooling 2D, flatten, dense 1 to 8, dense 10, soft max. So that's, and like for question 5, what each layer does. So like on 2D extracts features like edges and textures using learned filter. Max pooling reduce the image size while keeping the most important information. Flatten converts 2D features maps into a 1D vector from the dense layer. Dense 128 learns higher level patterns. Dense 10 softmax outputs a probability for each of the 10 classes. And next, if I go to question 6, for question 6, I added a second contour layer with 64 filters plus another max pooling layer. More convolutional layers let the network learn more complex abstract features. For question 7, I did the deeper model generally for question 7. The deeper model generally reaches higher validation accuracy because it can learn richer features. However, it also has more capacity, so it can like overfit slightly faster. Overall, it's a better model, but it needs a regularization, which brings us to like in question 8. For question 8, I added a dropout layer with rate 0.5 before the dense layer. So here is the dropout layer rate I add. And and this is the like model summary. And for question 9, the the dropout randomly turns off 50% of neurons during each training step. This stops the network from relying too heavily on any single neuron, forcing it to learn more robust patterns. Thinking of it like starting with half of my nodes randomly hidden each time. I forced to actually understand the material. The result is the gap between training and validation accuracy gets smaller, which means less overfitting and better generalization. So, the conclusion is in part A, we explored how different 2D kernels detect lines and edits in images. In part B, we build a CNN, identified overfitting, improved it with extra layers, and then reduced overfitting with dropout. Thanks for watching. That's all.